morning.
Good morning.
Good morning. All right, so today we're doing our Fractals presentation. This is class 18, Computer Network Support 1. Our first group is going to be Robert's group, and we're going to talk about fractals in nature.
Hi guys, my team Anthony, Alex, and Jasper's working not here with us today. Anyways, so we're going to start off about Fibonacci's history. So Fibonacci, he is an Italian mathematician. He's also known as Leonardo of Pisa. I'm not pronounced that fully. AKA also known as Fibonacci. He's the one who introduced it or made it known into the world. The Fibonacci sequence was first discovered by a mathematician in India about 1,300 years ago. He introduced it to the West in 1202 and also introduced the Arabic numerals to Europe, and that's why we use the numbers that we use today. And he also, with the Fibonacci sequence, he also came up with the phi, which is the golden ratio. So I'm going to dive a little bit deeper into the Fibonacci sequence. So basically, this chart tells you, so here's the numbers that is in the sequence, and how you get those numbers is by taking the last two numbers and adding them. So 1 and 1 is 2, 2 and 1 is 3, 3 and 5 is 8, so on and so forth. Fibonacci uses bunnies as an example to explain this. So basically there's two bunnies, one each, then those two do the thing. Then there's another one comes out, and you add those together, which is 3. Then those 3, after they do their thing, total is 5, and so on and so forth. Oh, so now we're going to talk about the phi, how that correlates with Fibonacci sequence. So basically, the bigger the numbers get in the sequence, when you divide those two together, it gets to 1.608. Close to that number, it's a really long, it's an irrational number, which never repeats. So this is what it looks like. I'm just going to dive in a little bit and show you guys how they came up with that number. So basically, to start, there's a line. So let's say right around there. This isn't a perfect example. It's close. So let's say this is A, this is B. So basically, phi is equal to A over B, which is also equal to A plus B over A. So basically, this is a 1 to 1.6 ratio, just give or take. So this is equal to 1.6 of that. So to continue with the math, this equation right here is basically equal to A over A plus B over A, which this equals to 1, and this is just the inverse of phi, which makes it 1 over, not that bad, phi. So, to continue off of there, so phi would equal to 1 plus 1 over phi. And this is the part that gets a little bit interesting, because basically, if phi is equal to this, this will go on infinitely. So it'll kind of look like this, where you try to solve it like this, it would just equal to 1 plus 1 over 1 plus 1 over 1 plus 1, so on and so forth, with phi being eventually at the end, which won't happen because it's infinite. So the way they solve for phi, they make it into a quadratic formula and solve for x, phi. And I'm going to show you guys how to do that now. Brain force. So basically, how you get this into that equation to solve it. So basically, the equation needs to be ax squared plus bx plus c equals 0. So how you get that into that equation is use the quadratic formula. You will multiply both sides by phi. So basically, it will go phi squared equals to phi plus 1, because this cancels out. And then you will move everything over to one side, which would be 5 squared minus 5 minus 1 equals 0. Then you use this equation, quadratic formula equation. Plug it in, and that will give you 5. And I'll show you guys how to do that now. So, before I go on, so basically with the a, x squared equals, or plus b, x plus c, you would get 1, -1, and -1, because this is the correlation ax. I don't know if you guys fully understand that. Was taught in algebra. But to plug this all into the equation, so x, which is technically 5 that we're solving for, is equal to 1 plus or minus square root of 1 squared minus 4 times a, which is 1, times -1 over 2a, which is 1. So 5 would equal to 1 plus square root of that equals to 5 over 2, which if you punch this into the calculator, it will give you that irrational number of 1.603, so on and so forth.
Take that 5 away from the x, because you're saying that you're multiplying.
Yeah. I was just trying to correlate or represent.
Yeah, I understand what you're saying.
Alright, so that's a good job. I got a couple examples too to show you guys how the Fibonacci sequence is on Earth. So this one's a hurricane, and as you can see, the Fibonacci sequence is correlated with this. So inside the eye of the hurricane is 0, 1, then it goes 1, 2, and then it goes 3, 5, 8, 13, 21, 34, 55, and so on. And the bigger it goes, the bigger the number it gets, as you can see. So basically that 5 sequence is just a spiral. So in the northern hemisphere, the deflection goes to the right, which is the hurricane, and in the southern, it goes to the left. So, and then it's not only just on Earth too, it could be in paintings too. And then in this one by Katsushika Hakuse in 1830, made a painting. As you can see, the spiral goes right here, and then inside that painting, there's also fractals in there too. You can see the little curves. Can you guys see that? Yeah, you see that there? That's how it's in paintings too. You can also see it in water, because in whirlpools, you can see that down there, that's where the eye of the whirlpool is, and if the variations of those, you can see in the bathtubs. You can put it, like you can see in the toilet when it flushes. You can see in the shell right here, the cone. And each, like most cones and most leaves and stuff like that, goes to like 5, 8, or 3, or 5, 8, and 13. That's where sequence come from. Each sequence is 1.61. And the next one. And then you can also see in the galaxies too. So in physical cosmology, fractal cosmology is a set of minority cosmology theories which state that this distribution of matter in the universe, the structure of the universe itself, is a fractal across a wide range of scales. As you can see, the galaxies right here, spirals. More generally, it relates to the usage of appearance of fractals in the study of the universe and matter. Essential issue in the field is the fractal dimension of the universe, or of matter distribution within it, when measured at very large or very small scales. And then, next one, you can see right here, a bunch of gas giants and molecular clouds, the galaxies observed by the fractal structures ranging. And the next one. And you can also see it in like the cosmic web, the human, and this right here is what you get where the Earth and the Sun move through the galaxies and swirls, you know. You guys seen it last time? That's about it.
Okay, so I will be talking about the coastline paradox to kind of get a better understanding of this. So if you were to measure the coast of the United States, you might think it's easy if you just outline the outside of it, but there's more into that. A lot of organizations and people, they test this out by, and all of them get different results. So for example, there's an organization called the CRIA, I think it's a Congressional Research Institute. They did 2 tests. First test, they got 12,383 miles, and then the second test, 29,093 miles. So both tests are different. CIA, they did the same test. test is around 28,000 miles. And then NOAA, that's the National Oceanic and Atmospheric Administration. They test this out. They basically study oceans and skies, and they got 95,000. So if you see these numbers, all those numbers are different. So that's kind of weird because why is it different? If you were to test or figure out the measurement of the coastline of Great Britain, you can see that these there's some straight lines. If you zoom into those straight lines, they don't come out straight, they come out curved. And then if you were to measure in length of 100 kilometers, you would get about like 28 of those, so 2,800 kilometers. But if you cut that in half of 50 kilometers, you get about 68, and that totals of 3,400 kilometers. So that's the coastline paradox. If you measure the length of a coastline, if it's small, you get a large amount in total. And this observation started by Lewis Fry Richardson in 1951. So basically, if you zoom into the coast, it doesn't always, it's not always a straight line. So the coast snowflake, if you were to have a triangle with equal lengths of 1, and then you put a triangle on top of that with equal lengths of 1/3, and keep doing that, and that process goes on forever. And as you can see here, that's the snowflake, but within that there's more to it. It just keeps adding forever and ever. And that kind of relates to fractals, because fractals are a pattern, a sequence of patterns that just goes on and on and on. And if you zoom out of the snowflake here, it's the same pattern that goes on and on. So measuring the coastline, you don't always get this, like everybody around the world, it doesn't always have an accurate measurement because coastlines always change. So for example, waves in the beach, waves that crashes in the beach, that changes the coastline. So if you were to measure coastline and you zoom in like in a small molecule, the numbers change a lot and it goes infinite. So you can never get an accurate measurement for that, meaning that the coastline, the true value is impossible.